Hello everyone, welcome to my YouTube channel, Usano-Goldie RL Marquez. This is my second video presentation of a lecture series in integral calculus. In this video, I will be discussing the general power formula for integration. Let me now begin with my presentation. Welcome to Integral Calculus or Calculus 2, Basic Integration, Section 1.2, General Power Formula for Integration. In evaluating any indefinite integral, it may not always be clear what particular formula or procedure to be applied. We assume that we have enough expertise to make a reasonable initial guess of what to do, but it does not require us to get absolutely right the first time. The methods of evaluating indefinite integrals are generally classified or categorized into two groups: basic or fundamental integration formulas, techniques of integration. We begin with the basic integration formulas. The following theorem, called the chain rule for integration, gives light to the understanding of the basic formulas that we will be discussing. Let G be a differentiable function whose range is an interval I. If f is a function defined on I, and that big F is an antiderivative of f on I, then the integral of f of g of x times g prime of x dx is equal to big F of g of x plus c. Or the integral of f of u du is equal to big F of u plus c, where u is equal to g of x with du equals g prime of x dx. The first basic integration formula that I'm going to tackle is the general power formula for integration. Let u be a differentiable function of x and n be a real number. Then the integral of u to the n du is equal to u to the n plus 1 all over n plus 1 plus c, where n is not equal to -1. Simple power formula. If u happens to be exactly a simple variable x and n not equal to -1, then this general power formula for integration becomes the integral of x to the n dx is equal to x to the n plus 1 all over n plus 1 plus c. Let us have this first example. Evaluate the integral of x to the 4th dx. This integral fits the simple power formula. Here, n is equal to 4. Hence, we have the integral of x to the 4th dx is equal to x to the 4 plus 1 all over 4 plus 1 plus c, or x to the 5th over 5 plus c. Example 1.2.2. Evaluate the integral of 3x squared times x cubed plus 5 quantity to the 4th dx. Let us express this integral in the form of u to the n du. Here, our u is x cubed plus 5, n is 4, and let's see if the remaining quantity will be the differential of this u. So from here, the differential of u is equal to 3x squared dx. So this integral is read as u to the n du. Since this integral takes the form of integral of u to the n du, so we can apply the general power formula. Hence, we have the integral of u to the n du is equal to u to the n plus 1 all over n plus 1 plus c. So where u is x cubed plus 5, so that is x cubed plus 5 quantity to the fifth all over 5 plus c. Another way to solve such integral is by the use of chain rule for integration, or that is by simple u substitution. The integral of 3x squared times x cubed plus 5 quantity to the fourth dx, when expressed in terms of u, is equal to, so this is our u, x cubed plus 5, and this is our n, 4. And since the differential of this u is 3x squared dx, so this means that this is exactly the du. So expressing this in terms of u, we have x to the fourth du. So the integral of this is equal to u to the fifth over 5 plus c from the general power formula. Let us express this u in terms of its original variable, that is in terms of x. So finally, we have x cubed plus 5 quantity to the fifth over all over 5 plus c. Let us have another example. Evaluate the integral of m cubed times m cubed minus 1 quantity squared dm. Potential u here is m cubed minus 1 with n is equal to 2. Let's see if the differential of this u is present in the integral. So the differential of this is 3m squared dm. Unfortunately, the differential provided in the integrand, which is m cubed dm, which does not match the differential of u, which is 3m squared dm. But if we expand this integrand, so let's expand. So this is a binomial. When we square it, we get m to the 6 minus, that is 2m squared. I mean 2m cubed, sorry. M cubed plus 1 times m cubed. So we get m to the 9th, so that is the first term in the expansion of this, minus 2m to the 6th, so that is the second term, and then the last term is m cubed times 1, so that is m cubed. So getting m to the 9th minus 2m to the 6th plus m cubed as the expansion of m cubed times m cubed minus 1 quantity squared. So we can apply a term-by-term integration here. So integrating the first term, we have m to the 10th over 10. For the second term, we have m to the 7 over 7 times negative 2. And for the third, m to the 4th over 4. We apply simple power formula to each integral. So the final answer is m to the 10th over 10 minus 2m to the 7 over 7 plus m to the 4th over 4 plus c. Another one, evaluate the integral of y cubed minus 3 square root of y plus 5 quantity squared dy. Let's try this expression as our u. Y cubed minus 3 square root of y plus 5. The differential of y cubed is 3y squared dy, while the differential of negative 3 square root of y is negative 3 over 2 square root of y quantity dy. Hence, the differential of u is equal to 3y squared minus 3 over 2 square root of y quantity dy, since this is 0. But this du is not in the integrand. So this suggests expanding the integrand and evaluating this integral by a term-by-term integration. So let us expand this trinomial quantity squared. How to expand this trinomial quantity squared? So that is actually squaring of a polynomial. So we square the first, so that is y to the 6 plus the square of the second, that is 9y, plus the square of the third term, that is 25. The next term is obtained by multiplying the first term and the second term, then times 2. So getting negative 6y to the 7 halves. Since square root of y means y to the 1 half times then y times y to the third, that is y to the 7 halves. The next term is obtained by multiplying the first term and the third term times 2, so giving 10y cubed. And then finally we have negative 3 times 5 times square root of y, then times 2, getting negative 30 y to the 1 half. So integrating this by a term-by-term integration, or evaluating this by a term-by-term integration, we have, for the first term, y to the 7 over 7, first integral. Second integral, 9 times integral of y dy is y squared over 2. The third integral, we have 25, so we apply here one of the general properties of indefinite integral, that is general property number 1. So that is simply y, then times 25. Then we have negative 6 y to the n dy. So we have y to the n plus 1, so plus 2 over 2. So 9 over 2, all over 9 over 2. So plus here we have y to the 4th over 4 times 10. And last integral we have negative 30. So y to the 1 half, integral of y to the 1 half dy, that is y to the 3 halves over 3 halves. So that is plus 1, which is 2 over 2. So that is 3 halves over 3 halves. Y to the 3 halves over 3 halves, 10 plus c. So simplifying, we get 1 over 7, y to the 7, plus 9 over 2, y squared, plus 25y minus, this is 6 over 9, that is 2/3, then times 2, negative 4/3, y to the 9 over 2. 10 over 4 means 5 over 2, so that is 5 over 2, y to the 4th. 30 divided by 3 is 10, so negative 10 times 2, so we have negative 20, y to the 3 halves, plus c. So that's it. Another one, evaluate the integral of ln of tangent 3x plus 5 quantity to the 6 all over tangent 3x cosine squared 3x dx. Potential u here is u to the equals ln of tangent 3x plus 5. So this is the potential u with n equals 6. So let's take the differential. So the derivative of ln is derivative of its argument. The argument is tangent 3x. So that is secant squared 3x, derivative of 3x by chain rule for differentiation. We have 3 secant squared 3x dx over tangent 3x for the differential of u. So again, the derivative of ln of tangent 3x plus 5. So this is 0. Derivative of ln is derivative of this. 3 secant squared 3x over tangent 3x. So that the differential is 3 secant squared 3x dx over tangent 3x. The integral of this is our u, this is n, but unfortunately this is not du. So there is a missing factor 3 for this to be du. We supply this missing factor inside here and then compensate it with a factor 1/3, meaning it's reciprocal outside the integral sign. Let us call this constant factor to be multiplied here, inside the integral sign, to complete the differential of u as a correction factor. So this is, when multiplied here, is called a correction factor. So let's do that. So for this integral, so our u is ln of tangent 3x plus 5 when n 6, and the differential of u is 3 secant squared 3x dx over tangent 3x. So we correct the differential. So we need 3 as a factor here, and then balance outside by its reciprocal, that is 1/3. So this is now read as integral of u to the n du. Since the sound is already u to the n du, so the integral of that is u to the n plus 1, so 6 plus 1 is 7, all over 7, and times 1/3 plus c. So let's simplify, getting 1 over 27, 1 over 21 times ln of tangent 3x plus 5 quantity to the 7 plus c. Using u substitution or by the chain rule for integration, we are going to express this integrand in terms of u. This is the u, and this is supposed to be the du. So, but this du can be written du over 3, which is equal to dx over tangent 3x times cosine squared 3x, because secant squared 3x is 1 over cosine squared 3x from the identity in trigonometry. So this expression is u, this is n, and this is supposed to be du over 3. So in terms of u, we have integral of u to the 6 times du over 3. So let's move 1/3 out of the integral sign. So integral of u to the n du. So the answer is u to the n plus 1. So that is 7 over 7 times 1/3 plus c. Let us express this in terms of its original variable. So we have in terms of x. So getting 1 over 21 in times ln of, so our u is ln of tangent 3x plus 5, 180 to the 7 plus c. So hence, the integral of this is equal to 1 over 21 ln of tangent 3x plus 5 quantity to the 7. Another one, evaluate the integral of e to the 2w arc cosine to the fourth of e to the 2w over square root of 1 minus e to the 4w dw. Let's guess the u. So I think it's arc cosine e to the 2w with n equals 4. Let's see if we will able to get the correct differential of the u, of the du, I mean. So the derivative of arc cosine is negative. So we have negative here. Derivative of its argument, so that is e to the 2w. Derivative of 2w is 2 over square root of 1 minus the square of this. So we get square root of 1 minus e to the 4w. So du therefore is negative 2 e to the 2w dw over square root of 1 minus e to the 4w. So let's check if this is present inside. So expressing this integral in terms of u, in terms of u to the n du format. So let's read the integral of u to the n, but unfortunately this is not du. So integral of u to the n, not du. For this to be du, we need to multiply it by negative 2. Correction factor is negative 2. So we multiply by negative 2. So this is now du. But of course, so that there is no change in the value of the integral, we compensate it outside by negative 1/2, the reciprocal of negative 2. So when we read this, it is now read as integral of u to the n, and this is now du. Since the sound is already u to the n du, so the integral is equal to u to the n plus 1. So from 4, it becomes 5 over 5 times negative 1/2 plus c. So we get, finally we get negative 1 over 10 arc cosine of e to the 2w quantity to the 5th plus c. So we just simplify this. So I just simplified that. Okay, so that's it. Another way to do it is by U substitution, of course. So using U substitution, our u is arc cosine of e to the 2w, n is 4, and the differential of u is what we had in the previous solution, is negative 2 e to the 2w dw over square root of 1 minus e to the 4w. So let us express this in terms of u. So this is u, this is n, and let's determine the value of this in terms of du. So we have du over negative 2. So if we divide this by negative 2, we get this expression. And then dividing the left side by negative 2 also, we have du over negative 2. Hence, this part is du over negative 2. So we get u to the n, which is 4, then times du over negative 2. Let's move the negative 1/2 outside the integral sign. So getting negative 1/2 integral of u to the 4th du. So the integral is u to the n plus 1. So this is now 5 over 5 times negative 1/2 plus c. So of course, we have to put this back to its original variable. So u in terms of x, we have arc cosine of e to the 2x, then raised to 5, and then this is 10, so negative 1 over 10 arc cosine to the 5th of e to the 2x plus c. Okay, so that's for such integral. So let us have this last Evaluate the integral of secant squared 3t dt over 4 plus tangent 3t quantity to the 5 over 3. So let's try this expression as our u. The differential is equal to derivative of 4 is 0. Derivative of tangent is secant squared 3t. Derivative of 3t is 3 times dt to be the differential of u. So let's express it in the form of u to the n du. So we have 4 plus tangent 3t. When we bring this up or we bring this in the numerator, it becomes to the negative 5 over 3, the exponent. And then this is the possible differential. Unfortunately, again, there is a missing quantity, which is a constant. Now, take note that if the missing quantity to complete the du is not constant, containing variable, so we cannot introduce a quantity with variable inside and then balance it by its reciprocal outside. Only constant is allowed. So to complete the du, so we have this correction factor 3. So we have corrected now the du. So this is u to the n du. But of course, there is a change. So that there is no change in the value, we multiply outside by its reciprocal. Actually, this is general property of indefinite integral. Number, if we recall, number 3. So this is now read as u, integral of u to the n, and this is du. U to the n, and this is du. So u to the n du. If it is u to the n du, the integral of that is equal to u to the n plus 1, so plus 3 over 3, negative 2 over 3. So 4 plus tangent 3t quantity to the negative 2, 3 over negative 2, 3 times 1/3. So 3 times negative 2/3 is negative 2, so negative 1/2 times 4 plus tangent 3t quantity to the negative 2/3, or negative 1 over 2 multiplied to 4 plus tangent 3t quantity to the 2/3. So if you want the exponent to be positive, plus c. Okay, that's the final answer. That's the integral of secant squared 3t dt over 4 plus tangent 3t quantity to the 5 over 3. So another way, of course, is by the use of substitution. So we have du is equal to 3 secant squared 3 dt coming from this u. So let us express the given integral in terms of u. So this is du over 3. So coming from here, we solve secant squared 3t dt. So that is du over 3 divided by 3 divided by 3. We get this quantity. So the numerator is du over 3, the value of this in terms of u. Then the denominator is u to the 5 over 3. U to the 5 over 3. So getting 1/3. So let's put the 1/3 out so that we have u. We bring this up, u to the negative 5 over 3 du. So from one of the laws of exponent. So the integral of u to the n du. So if the sound is integral of u to the n du, what's the answer? U to the n plus 1 all over n plus 1. Yeah. But don't forget to multiply by. So let's multiply by 1 over 3. Yeah. So let's multiply by 1 over 3. So getting 2 over 3u to the negative, u to the 2/3. But 3 will cancel, so this now will disappear, and this 2 So let me correct this one. Sorry for this. So this is supposed to be equal to negative 1/2. 1/2, and then u to the negative 2 over 3. 2 over 3 plus c. So expressing this in terms of its original variable, in terms of function of x, we get 1/3. Yeah, that's 1/3 u to the n, which is plus 1, which is negative 2/3 over n plus 1, negative 2/3 plus c. So that when simplified, actually that is already negative 1/2. So negative 1 over 2 multiplied by 4 plus tangent 3t quantity to the 2/3. Oh, we have another one. I thought it was the last, so let's have this. Evaluate the integral of cosecant squared 2x minus 5 hyperbolic sine 2x. This is multiplied to fifth root of 5 hyperbolic cosine 2x plus cotangent 2x dx. Possible u, we have 5 hyperbolic cosine 2x plus cotangent 2x with n equals 1 over 5. So then du is equal to, so the derivative of hyperbolic cosine 2x is hyperbolic sine 2x. Derivative of 2x is 2 times 5, so we have 10. For cotangent 2x, the derivative is negative cosecant squared 2x times derivative of 2x is 2. So negative 2 cosecant squared 2x. So multiplied by dx. So that's the differential of, to be differential of du. So this is u to the n, but unfortunately, again, this is not du. So let's fix this. So solving for this quantity, we want to form this one. So we have to divide this by negative 2. If we divide this by negative 2, this becomes positive. So we now have, so this is already 1, so no more this. So let us erase this part. So again, divide by negative 2, we have positive cosecant squared 2x. This term, when divided by 2, we have negative 2, we have negative 5. Dividing by negative 2, so we have now 1 divided by negative 2, negative 5 here. So that du over negative 2, when divided by 2, negative 2 also, we have du over negative 2, that is equal to cosecant squared 2x minus 5 hyperbolic sine 2x quantity dx. So this part is du over negative 2. So in terms of u, we have u, so this is u, this part to the n, and this is du over negative 2. Factoring out negative 1/2, so meaning put it outside the integral sign, we get negative 1/2 integral of u to the 1 over 5 du. So this takes the form u to the n du. So the integral is u to the n plus 1, so plus 5 over 5 over 6 over 5 times negative 1/2 plus c. So 2 times 6 over 5 means 5 over 12 times negative, so negative 5 over 12, and u is 5 hyperbolic cosine 2x minus cotangent 2x quantity to the, this is the n plus 1, 6 over 5 plus c. So that's the final answer. Okay, so that's the last. Thank you for watching. Please don't forget to subscribe to my YouTube channel, Usano-Goldie RL Marquez. For the next video, lecture notes 2, general power formula for integration part 2. So I will be discussing more examples, more challenging problems, applying general power formula together, of course, with some of the general properties of indefinite integrals. Bye.